So if you know Gilad, you will have noticed that I don't look like him. That's why they asked me to give this presentation, but I'm not on the paper. And so, I mean, if you have very kind of technical questions, maybe, yeah, ask them. I mean, but I do know the proofs. Right, okay, so what's the main goal of the talk? So, you know, like the title is kind of takes inspiration from this famous work by Michal Ordetsky, Jonathan Oppenheim, and Andreas Winter on quantum state merging and negativity of conditional entropy. And so that was kind of, yeah, knowing less than nothing means like negativity of the conditional entropy. That's the way to interpret it. So, okay, so what's the main goal of the talk? So like to kind of give an axiomatic approach to the definition of conditional entropy, okay, of quantum conditional entropy. And so in particular, we'll give like two axioms that imply that the conditional entropy satisfies certain properties. And in particular, that it gets negative on certain entangled states, okay, on the maximal entangled state in particular. And so, so that's why inevitability of knowing less than nothing. So that's the title. Okay, so what's an axiomatic approach to entropy? Let's start with the simplest case in which you have, instead of the conditional entropy, just the entropy, and not even quantum, just classical. Okay, so the Shannon entropy is uniquely defined by some axioms, and if you basically consider one, you drop one of the axioms, you get another family of entropies. It's also very famous, the family of Renyi entropies. And so you can ask yourself, why are these quantities kind of natural, and could there be other interesting entropies that satisfy also these axioms, right? And so it turns out that under two very natural axioms, basically, it turns out that all entropies are of this form, either the Renyi entropies or the Shannon entropy, which is a special case of the Renyi entropy. Okay, so and to understand why these axioms make physical sense, you want to look at what is a mixing operation. Okay, so a mixing operation is an operation that acts on probability vectors. So mathematically, so this is a probability vector, and so this will be a linear matrix that acts on probability vectors. Like it's basically a convex combination of permutations. Okay, so you kind of you switch the labels of your alphabet, and you kind of forget how you switch them. And so. Oh, I see. Okay, right. I mean, so and mixing operations, of course, they live invariant the uniform state, right? So the uniform probability distribution, because of course permutation doesn't do anything. So mathematically, this means that M is so like this form of M means that it is doubly stochastic. Okay, it's a doubly stochastic matrix. Right. So what is an uncertainty measure? An uncertainty measure is a collection of functions, right, from the set of all probability distributions over discrete alphabets, and right. So discrete finite alphabets, right, and the axiom that we want to make is that it never decreases under mixing operations. It can always increase, only increase. Okay. So this is called that also Schur concavity. And what is an entropy? Well, it's a collection of functions over all probability distributions over all discrete alphabets, so all finite alphabets. So these are the probability distributions over an alphabet of size n, and you basically take all of them, all of the finite alphabets. And so it has to satisfy two axioms. The first one is that it's an uncertainty measure. So uncertainty measure means exactly this, that it's increasing or non-decreasing under mixing operations, and also it has to be additive under product distributions, okay, under product of distributions. So this is what in probability theory one calls, independent random variables. So when you see like this kind of uncertainty, so the mixing, the monotonicity under mixing is kind of something that relates, it's a property of the function just defined on this space for fixed n, because mixing never increases n somehow. But this one kind of relates the different levels of the function. So it characterizes this family of functions as a whole. Okay, so what are the consequences? There are several consequences. The first one is that the entropy is non-negative for all probability distributions, and it is equal to 0 for the deterministic ones, okay? So the degenerate ones, like 1, 0, 0, 0, okay? You can derive this as a consequence of these two axioms, and the other consequence is that it is maximal for the uniform probability distribution. And okay, so as usual, you can fix the unit. So for example, you can normalize it, like rescale it, so that it is equal to 1 on the uniform probability distribution of an alphabet of size 2. And then you get also for free from the axioms, from additivity in particular, that it is equal to log d over all probability distributions, uniform probability distribution over an alphabet of size d. And in fact, you can prove a theorem, like it has been proved in this work in 2021, that all entropic functions, so all normalized entropy functions, so that satisfies these two axioms, monotonicity under mixing and additivity, they are all convex combinations of Renyi entropies. Okay, so in particular, there is nothing more than that. So like, I mean, convex combinations is kind of a trivial thing that you can do to mix two functions that are already entropies, and that's basically that's all. Okay, so now let's look at quantum entropy. Let's proceed by steps. Okay, so what is a quantum mixing operation? Well, there is a clear answer, or well, a natural answer, let's say, like those operations that preserve the maximally mixed state. Okay, so the identity, basically the normalized identity over finite dimensional space. This is called the mixing operation. And what is a measure of uncertainty? Well, it's a collection of functions over all density operators over finite dimensional systems. And we want to assume that this is non-decreasing under mixing operations. Okay, so the entropy cannot decrease if you relabel and forget about the relabeling, because that's going to increase to your uncertainty. Okay, so these are the two axioms for the quantum entropy. They're exactly kind of equivalent to the ones we saw before, right? So the uncertainty measure, so monotonicity under mixing, quantum mixing operations, so unital channels. And then additivity. Okay, in this case, you have the familiar tensor product between actual density operators. Okay, so and under these axioms, you can prove again a theorem which is like you can derive some consequences that are more or less like the ones we saw before. So non-negativity of all on all quantum states, and and then the value has to be equal to 0 for pure states. So these are pure states are of course like the same as this deterministic probability distributions. And then again, you can find that it is maximal on the maximally mixed state and equal to log d if you renormalize it. Okay, so now the real deal, which is quantum conditional entropy. Okay, so in this case, you have a bipartite quantum system, a density operator over a bipartite quantum system. And again, you will have a collection of functions over all such systems. And this time it's a real function. This time it will take on negative values. This is the way we are going to denote it. So A will be always the system, the conditioned system, and B will be always the conditioning system. Okay, so some intuition from classical. So what the conditional entropy basically measures the remaining uncertainty on the conditioning on the conditioned system, given the knowledge extracted from the conditioning system. Okay, so you know. So for example, the conditional entropy of x given y is whatever uncertainty remains on x given the information on y. Okay. And if x and y are independent, of course, like knowledge of y doesn't imply any knowledge on x. So that should give you an entropy on x. Okay. So the entropy should be equal to the conditional entropy in this case. But instead, if they are dependent, then some knowledge of y can inform you about the value of x. And we also assume that it is additive for independent trials. Okay, this is also fairly natural. Okay, so you remember we had this notion of mixing operations, those that preserve the maximally mixed state, right? For quantum entropy. For conditional entropy, you need to have a notion of kind of maximally conditionally mixed somehow, and this is a reasonable definition. You take the maximally mixed state on A, tensor product any state on B, and this has to be a state of kind of maximal uncertainty, right? Because they're independent, so you don't gain anything on A by knowing B, and the system on A is already maximally mixed. Okay, so the key notion for the paper is this notion of conditionally mixing operation. Okay, so there are several. Well, in the paper there are at least two approaches, but let's describe one. Okay, so what is a conditionally mixing? First of all, it has to be mixing. So like like if you take a state of the set and then you apply the channel, the output has to be also in this set. But there is also another condition that they assume in the paper, and they justify it also, which is semi-causality. Okay, what does semi-causality mean? Well, intuitively, it means that no information from A travels to B. Okay, so they're kind of, there is no causal link somehow. Let's try to make this mathematically precise. And the way to make it mathematically precise is like this. So you have a channel acting on a bipartite system AB, and you trace out the output A. So now what I want is that no information from A flows to this B system. And so then basically the output state on B prime should be independent of whatever input I get here, if I trace out A. So, and this equality means exactly that, because it tells you that if you trace out A, so that's this black square, whatever operation you do at the input on A, it doesn't matter. The state on B prime is unchanged. Okay, so there is kind of no information about this channel propagates to this B prime. So you can do anything there and it doesn't matter. Okay, so there is a theorem. You can use this axiomatic characterization to prove a theorem. This was done in 2002 by Egeling, Schlingemann, and Werner. And the theorem tells you that channels that are semi-causal in that sense are exactly those that are of this form. So basically there is some pre-processing on B that outputs two systems, one register R and the actual B output. And the register R is fed into an operation that takes A as an input and outputs again a system A, a different state, right? And of course, it's clear that these operations are semi-causal, because if you trace out A, this channel disappears, the output over A gets traced out, and you get just the output over B, and partial trace also over R. What is non-trivial, of course, is that all semi-causal channels are of this form, but that's exactly what they prove. Okay, so what is a quantum conditional entropy? Well, again, is a set of functions, right? One for each level, one for each pair of systems, A, B, finite dimensional. And it has to obey monotonicity under conditional mixing. Okay, so under conditionally mixing channels, and also additivity. So that relates the various levels of the function. Okay, so there are very many quantum conditional entropies in the literature. For example, most famous one is the von Neumann one. It's just a difference of the entropies, AB minus B. But there are also more complicated formulas. There is a host of formulas, in fact. And another one, very famous one, is the Petz-Renyi conditional entropy, which is defined for some real non-negative parameter alpha, which can be also infinity. And it's defined by this complicated, if you want, tracial expression. Okay, so these are perfectly valid quantum conditional entropies in the sense that they obey these two axioms. And so there is also another special one, which is the conditional mean entropy, which is defined like this. So you take your state rho AB, you take this, the marginal on B, you tensor with A, and this is it's a state of maximal uncertainty, if you want, anomalized, and you look for the minimal lambda such that this operator inequality is obeyed. Meaning that if lambda is very small, then this is the two states are kind of equal up to normalization on A, so that means that the entropy is very large. The conditional entropy is very large, and so then you take that's why you take the minus the maximum of a lambda of minus log, or the minus infimum of the log. If you stare at it for long enough, it will make sense, I promise. Not too long. Okay, so and that's the main result of the paper. That's exactly that. The conditional entropy is lower bounded by this mean conditional entropy. So any conditional entropy. Okay, so any function that obeys the two axioms that we saw before is lower bounded by this mean entropy. And the bound is attained for the maximally entangled state. Okay. And then, of course, since you can compute this expression for the maximally entangled state, it's a pretty easy exercise. So that means that for the maximally entangled state, you get an equality, and you get that the right-hand side, and so also the left-hand side, is minus log of the dimension of A. So this is why it's kind of inevitable that this function will take on negative values. Okay. Right, and there is a simple corollary of this, which is that all all conditional entropies for a given state, all conditional entropies are non-negative if and only if the state obeys this operator inequality. And this kind of it's a immediate rephrasing it's an immediate consequence of this theorem. And so this is known as the reduction criterion. It turns out that every separable state satisfies this. So if you have a separable state, it will obey this inequality too, and that means that one will also hold, thanks to this corollary. And so that also, a way to rephrase this is that only entangled states can have negative conditional entropy. Okay? If a state is separable, it obeys 2, then it obeys 1, and then it's a positive conditional entropy. Okay. Right, let's look at some consequences. So we saw this one is non-negative for all separable unentangled states. It's just the same. And it must be negative for some entangled states. And it turns out it reduces to the entropy to some entropic function, like it could be von Neumann, it could be something else, for product states. Okay, so if you take a product state, then the state on B doesn't play any role. In fact, and this is just a function of rho A. And it turns out to be an entropic function in the sense we defined previously. And then it is maximal on the set of kind of conditionally maximal mixed state. Okay. And it is lower bounded by the conditional mean entropy. So that's a main result of the paper. They have two versions of it, depending on exactly how you define conditionally mixing channels. But this is the version that I'm discussing, and that's okay. So there are some open problems that are really kind of neat to state. So I really invite you to look at them. Right. So first of all, we don't know what the preorder among density operators induced by these conditional mixing channels looks like. So we don't know. So given two density operators, we don't have a criterion that tells you when there exists a conditionally mixing transformation that maps the first one to the second one. And we do have this for classical systems, but just the proof doesn't work for quantum systems. Don't ask me why. So, and the other thing is that they found lower bounds on the conditional entropy, right? In terms of this mean conditional entropy, it is very natural to look also at upper bounds. And there are several candidates in the literature, like the max conditional entropy, for upper bounds. But somehow the argument doesn't really carry over to that case. And with that, I thank you.
Okay, so do we have any hard technical questions for the speaker? Is it hard?
Thank you for the very interesting talk. So my question is in the beginning when you were listing the axioms. Okay, for the ones of Shannon, I understand. Basically you got this B-stochastic matrix because it's convex combination of permutation. However, when you're treating the quantum, you got the unitary and not convex combination of unitaries. Yes. What would also be a fair analog. And we know that, well, if it's not qubits, like they're different. So
no, I know. So I think that...
How can you justify and why?
So I think it actually doesn't matter. I think you can take also, because like the transformations themselves are different. This conditional, unital channels and of course like random unitary channels. But the ordering they induce on the density operator is just the majorization, and that's the same ordering. Okay. So this is why this doesn't matter. Okay. Jonathan wants to add something.
What's the other definition of conditional mixing? And you mentioned there are two definitions of conditional mixing.
Yes. So
can you say what the other one is and whether the same implication would hold?
They drop the semi-causality axiom. And so then you get a theorem that is analogous to what I stated, but instead of this conditional mean entropy, you get the other version of the conditional mean entropy, the one that the one in which you optimize over the marginal also. So you get
and do you also get that at all states that there is always a negative?
Yeah, you do, yes.
Other questions? Yep.
So as far as I knew that it was already known that the mean entropy was the lower bound of the entropy, right? So
it is known. I mean, it was known that the conditional mean entropy is a lower bound on the von Neumann entropy, conditional entropy. But the point is that we don't want to assume von Neumann, we don't want to assume Petz-Renyi, we don't want to assume anything. We just state some axioms and derive a lower bound.
I see.
And we don't have a characterization for this I mean, unlike for the classical case, we don't have a characterization for this conditional quantum entropies. Like we don't have like a thing like they are all convex combinations of the Petz-Rennies and stuff. We don't have this. So
Okay. Yeah. Thanks.
So thank you for the nice talk. So in this talk, you pay attention to the mixing process in order to define entropy. On the other hand, so for example, von Neumann entropy can be defined by measurement process, a kind of optimization of measurement process. How about such a characterization in your definition?
I think that's a reasonable approach. I don't think they take it in the paper, but so you're saying let's look at basically let's do a measurement on the quantum system, and let's consider all classical entropies on the outcome, and then let's optimize over the measurement. This is called like observational entropy, right? And like GPTs, for example. So, yeah, I mean, they don't consider this in the paper, but I think this is a reasonable approach.
Thank you so much.
So thank you for the talk. So if I understand correctly, you said that no matter in which way you try to define this conditional entropy, you will always find some entangled states that is giving you negative. So it's kind of a two-part question. So does there exist entangled states which will always be positive?
Yeah. This is, I think you. In general, I don't know actually. Yeah, but there are entangled states for which the mean entropy is positive, so that do not violate the reduction criterion. So in particular, for like all conditional entropies will be positive by their theorem.
Yeah. So part two of my question is, for example, you have this local entangled states. So what would happen for those?
Local entangled states?
Means entangled states which have a local hidden variable model.
Yeah, okay. No, exactly. I mean, you need some weakly entangled state. I don't see a clear connection with the local hidden variable, but you need a weakly entangled state. So like an entangled state that doesn't violate the reduction criterion. And we know the reduction criterion is, say, it's weaker than the PPT criterion. So, for example, any PPT entangled states, and there are plenty of those, will give you an example.
Oh, okay. I see. Thank you.
Can you pass it? Is it a comment on the question or it's another question?
I guess it's a follow-up to the question about the measured conditional entropy. So that's not negative. Is there one of the assumptions that it violates?
Yeah, no, exactly. I mean, like if you do conditional, yeah, then it's a bit more. I was just talking about like the standard entropy. Yeah, I mean, if you do conditioning, then yeah, I mean, you don't want you don't want to measure everything, otherwise you will get a positive conditional entropy, and that's not good.
But that's a reasonable definition of a conditional entropy? So does it violate one of their assumptions?
Yeah, I think so, because it's never negative, right? Because they're conditional.
Do you know which one it violates?
Well, I think it's. Wait a second. Not off the top of my head. No. But it must violate one of them.
Hi there. Thank you for the talk. So you had mentioned here that there's these entangled states that have negative entropy, and also some entangled states that have positive entropy. Mm-hmm. Is there some sort of intuition I should be having as to what would make an entangled state have negative entropy? I understand normally in conditional entropy it sort of gives you the number of uncertain bits that you have left in this.
So like best intuition I have is from the paper by Jonathan, Michael, and Andreas, that if you have a state that violates the reduction criterion, you can distill it.
I see.
So
okay.
So yeah, I mean yeah. So and if you have actually also von Neumann negative conditional entropy, you can actually one-way distill it. So you can distill it with one-way LOCCs. So that's the whole point of the paper, of course, and.
I see. Okay.
And yeah, this is kind of.
Gotcha. Thank you.
Maybe if there's one last brief question, we can take it. If not, okay, cool. So let's thank the speaker and the authors.